at the appendix. And what the appendix does is gives like an example with Cobb-Douglas of kind of going through these steps. But again, in a general sense, with specific numbers and for A and B. So let's do an example. And I think I'm going to try to like split the board in two here. Kind of work here, and then I'll work over here. So maybe we can finish it in one kind of board. So let's pretend our production function is a Cobb-Douglas production function. We have x1 to the A, and x2 to the B. Okay, so our maximization problem is to max the price times f of x1, x2, minus w1, x1, minus w2, x2, and we get to pick x1, x2. So here, we're just going to plug in our production function there. So our problem essentially is max x1, x2, those are our choices, p, x1a, x2b, minus w1, x1, minus w2, x2. We have two first order conditions. So we're maximizing, so we have two first order conditions. So the maximization, the derivative with respect to x1, well that's just a times p, x1, a minus 1, x2b. So x2 is like a constant and p is like a constant, right? So we're just taking we're using the power rule here, right? We're just taking the derivative, moving the a down, and just subtracting 1 from the exponent. So that's the derivative of this first term, the partial with respect to x1. And now we just have this, kick it around, equals 0 at the max. And then we're going to have the same thing, but taking the derivative with respect to x2, which is b times p, x1a, x2b minus 1, minus w2 equals 0. So those are our first order conditions. Now, here's a little trick that the book uses, but we're going to multiply this by x1 and multiply this by x2. And then we're going to get this, xp, x1 to the a. So for multiplying this by x, like this minus 1 will go away, right? We're going to add an exponent. So x2 to the b minus w1 x1, because we still got to multiply this term by x1 as well, equals 0. And if you think about, well, this is just the production function, right? This is just y. So another way of writing this is AP times y minus w1 x1 equals 0. And we can do the same thing. So this is this first term that we're working with here. We could do the same thing for term 2. If we multiply that by y, we get bp times y minus w2 times x2 equals 0. And then we can think about what our demand functions are. So we're just going to solve each of these for x1. Well, let's do the first one first. AP times y minus w1 x1 equals 0. That means w1 x1 equals AP times y, which means x1 equals APY over W1. For the second one, kind of just a trick to sub y in there, I guess. Sorry, the second one is BPY minus W2 X2 equals 0. for W2 X2 equals BPY, or X2 equals BPY over W2. So here are two demand functions. We want to figure out output. We plug, so these are the stars, I guess we should put, X1 star and X2 star into the production function. And if we do that, we're going to get something kind of ugly. So let me erase this, and we're going to plug these two terms back in for this. Okay, so on the last board, we figured out what the optimal amount of each of the inputs was. But maybe we want to figure out what the optimal output is. And that's going to be f, the production function, at these optimal amounts of each of the inputs. And here we know y equals x1 to the A, x2 to the B. So we're just going to plug in our x1 star here, our x2 star here. So our optimal amount of output, A times P to the Y, so P times Y I should say, W1 to the A, B times P times Y over WP to the B. And we want to solve this for Y. So we're trying to isolate Y. So it's going to be like a little bit tricky here. First, let's move Y out of the brackets. And so we're multiplying Y to the A and Y to the B. So if you remember our exponent rules, that's going to be Y to the A plus B, right? Then we have A to the P over W1, that's still to the A. And we have B times P over W2, and that's still to the B. And now we need to isolate this Y, and so we're going to divide both sides by Y to the A plus B. So if you remember again our exponent rules, remember it's like a Y to the 1 there. So if we're dividing both sides by Y to the A plus B, it's like we're subtracting these exponents, right? So it's Y to the 1 minus A minus B equals A to the P over W1 times A, B to the P times W2 times B. Let's work our way back up here. And now we want to isolate for Y. So it's Y to the 1 minus A minus B. And so if we took everything on the right-hand side to the exponent 1 over 1 minus A minus B, we'd get rid of this. I'm just going to put a star on it to show us the optimal amount. But now it's going to be A times P over W1. Hopefully this is on the screen. So this is in brackets. And it's going to be, let's put the other one in here, B to the P, W2 over B over 1 minus A minus B. And so this is our expression for the optimal amount of output in this kind of general Cobb-Douglas kind of framework. So notice it's undefined. If A plus B equals 1, which is constant, returns to scale, we actually have this undefined output. And that's because it doesn't matter with Cobb-Douglas. The level, it's indifferent towards supply. Basically, it just doesn't matter what level you're producing at because it's kind of, firms are indifferent to the level of supply. As long as like prices and inputs and stuff like that are consistent with the zero profit condition, it doesn't kind of, doesn't matter what level we're producing at. Okay, so again, this is like lots of algebra and lots of math, but in our practice questions, we're going to practice just applying it this week with like maybe a bit more numbers, but then maybe some functions as well, so you have to get some practice kind of solving this stuff more generally. So it's kind of somewhere between that is kind of what we usually do on test or exams. So let's kind of practice that this week. So I'll post some easier ones with actual prices, and then we'll do some general ones where we're kind of solving this generally.